Hi everyone, in this part of the video, we will be naming the ternary salts, binary acids, and ternary acids. So in the first two videos, we were talking about how we name binary ionic and binary covalent compounds. Now what if the compound isn't binary anymore, meaning to say it is made up of two or more than two types of atoms, okay? So this is where polyatomic ions come in. Okay? Polyatomic ions are charged entities composed of several atoms bound together. They are covalently bonded and they usually participate, those charged entity as a whole participates in covalent bonding. And here are a few of those polyatomic ions. Okay, so you have then nitrate ions and the nitride, the sulfate and the sulfide. So if you've noticed, in the naming, the one with the more number of oxygen atoms usually takes the ATE form, okay, 8, and then while the lower one uh, has ITE, the ITE form. So it has something to do with their oxidation numbers later on, okay, the kind of sulfur, the sulfur with the higher oxidation number takes the ATE form, okay, but we'll discuss more on that later. So another one is hydroxide, which is basically what makes some compounds basic, okay, OH. So you might have not noticed some active ingredients, sodium hydroxide, potassium hydroxide, magnesium hydroxide, okay. So most of them are bases, meaning they are bitter, they are slippery, and yeah, they neutralize acids. You also have more complicated ones like the acetate ion, okay, which is used in acetic acid, which is primarily found in vinegar, okay, 5% acetic acid, that's vinegar. And we can also have dichromate, chromate, which gives us very good colors, yellow to yellow-orange colors. Peroxide, so you might have noticed in wound treating, so hydrogen peroxides, but it's not so advisable right now. Okay, so how do we name ionic compounds? Naming ionic compounds containing polyatomic ions follows rules similar to those for binary compounds. Okay, so we just get to name the cation and then the anion. So for example, here is ammonium acetate. NH4 plus is our ammonium ion, while C2H3O2 is our acetate ion. So you might have noticed that when you crisscross and disregard the sign, you end up with the formula NH4 C2H3O2. Okay, so we just name them accordingly according to how they are named as polyatomic ions. So this is ammonium acetate. Right? Now a few examples also. So it is good if we have our list of polyatomic ions, or you can look them up, okay, but these are the most familiar ones. So NaOH, that is made up the sodium ion, and OH is a hydroxide ion. So the chemical name for NaOH is sodium hydroxide. All right, next one, MgNO32, that's magnesium nitrate. Okay, so you might have noticed that this is enclosed, the nitrate ion is enclosed in a parenthesis. So let me just explain a bit. This is a result between the bonding between the magnesium Mg, and we know that magnesium can form Mg2 plus ion, that cation, right? Then the nitrate NO3, that's our nitrate ion. So it helps if we are familiar with the chemical formulas of the polyatomic ion. So what we did here is to crisscross, then disregard the sign. Okay? Some people are led to think that the 2 will just be right beside 3 here. Alright? But it's actually for the whole group. Okay? For the whole NO3 ion, meaning to say in that particular compound there are two groups of nitrates. Okay, there are two functional groups for nitrate. So that's why we must enclose it in a parenthesis. That's NO3, close parenthesis 2. Okay, that's also to separate the two subscripts from going together. Alright, so that's magnesium nitrate. This one, the third example, is a result of ammonium ion, rather, sorry, NH4 plus, and the sulfate ion, SO4, 2 minus. Right? So NH4 plus, SO4, 2 minus. So the same principle here. If we place 2 and disregard the sign, it must be for the whole group. So our name for that compound is ammonium sulfate. Alright? NH4 sub 2 SO4. Now try to look at this one, FePO4. Okay? So you must be familiar that there are some polyatomic ions which can cancel out the charges or reduce to lowest terms. Okay, once they meet up with a particular cation having the same charge. For example, in this compound, this actually came from Fe plus 3. And how do I know that? How do you know that, sir? Well, if you know the charge of the phosphate ion, the PO4, if you try to look it up in your list, you'll know that it has a charge of 3 minus or minus 3. Okay? So if you crisscross and disregard the sign, you end up with Fe3, supposedly PO4 sub 3 for the whole group. But we know that this is ionic bonding, so we get to cancel or to reduce it to lowest terms. So we end up with FePO4. And the name for that compound is iron 3 phosphate. Okay, iron 3 phosphate. Since this is iron 3, the component cation is iron 3 plus, and you have the phosphate ion. Okay, so maybe you can pause this. What is the name of the compound? KClO3. That is potassium chlorate. Okay, potassium chlorate. So it came from the K plus, which is potassium, and the ClO3 minus. Okay, so that's potassium chlorate. Now in this part, we will be naming, let's make it a whole already, we will be naming acids, okay, so which is also a very important part in chemical nomenclature. So again, we can consider them to be binary or ternary. Okay, so acids can be recognized by the hydrogen that appears first in the formula. Okay, so for example, HCl. Then it's a substance with one or more H plus ions attached to an anion. Okay, so this is a special class, and there is a set of rules for naming binary acids. So here, if the acid is in its pure form, okay, meaning it's you do not see any subscript here. You don't see any subscript, so it can either be a gas or a pure liquid. So you can have G or you can have L. It depends on the nature. Then in naming them, we can just have hydrogen plus name of the anion. So for example, hydrogen chloride, okay, hydrogen bromide, hydrogen sulfide. Okay, so you do not see any subscript that or you can just see L or G that denotes that they are in their pure form, just hydrogen plus the name of the anion. However, something happens if we see this AQ. This means or this denotes that the acid has already been bubbled or mixed with water. So aqueous AQ means aqueous, from the word aqua. Okay, so that means it is mixed with water. So when that happens, the way of naming changes. So for binary acids dissolved in water, we use hydro plus stem of the nonmetal plus ic acid. Alright, so for example, instead of hydrogen chloride, then we see this subscript here, AQ, then we say hydrochloric acid, okay, if it's mixed with water. Hydrobromic acid, hydrosulfuric acid, and this is a special case. It's not binary, but this is a is one. This one is considered as a polyatomic ion. Okay, the cyanate ion. So we call this a hydrocyanic acid. Okay, it's an exception. Now, for those acids containing oxygen, or we call them oxoacids. Once they are in their pure form, then we just write hydrogen and then the name of the polyatomic ion, hydrogen nitrate, hydrogen sulfate, hydrogen acetate. Okay, so this is the sulfate ion, C2H3O2 was mentioned a while ago. This is the acetate ion. Okay, you do not see any aqueous there in their formulas. However, once they are mixed with water, there can be two types. Okay, so there's another type of naming. So if the anion contains oxygen, first the suffix "ic" is added to the root name if the anion name ends in ate. Okay, so for example, NO3 minus. NO3 minus is our nitrate ion, right? So we know that the name of this ion is nitrate, so we follow this rule. Okay, we replace ATE with IC. Okay, the same thing with the other examples. So we change this into ic, and we no longer place hydro. Okay, the hydro is just for the binary, which are dissolved in water. So this is nitric acid, sulfuric acid. You see the AQ there. This is supposed to be sulfate. Okay, so sulfuric acid. This is acetate, but it has AQ, so we say acetic acid, or the more correct pronunciation is acetic acid. Okay, now if the anion contains oxygen, still the suffix is os, OUS, if the anion name ends in ITE. So these are the ones with lesser oxidation numbers, so lesser number of oxygen. So a while ago we were talking about NO3, so what if it's NO2? So we now have nitrous acid, sulfurous acid, and chlorous acid. Alright? So there are also some examples na CLO na lang siya. Okay, so there's a special name for that, specific for that particular polyatomic ion. Alright? So flowchart for naming acids. Does the anion contain oxygen? If not, then you follow the rules, hydro, and then anion root, or ic. Okay, so hydroiodic acid, hydrochloric, so on. And then if it has oxygen, then remember the ate or ite. So if it's ending in ate, it ends with the ic, no hydro already. If it's ite, then it ends in os. So let's practice what we were talking about in the two classifications. So HF. So we assume that this is in its pure form because there is no aqueous subscript. HF is hydrogen fluoride. Na2CO3, so this is a ternary salt. Okay, this is not an acid, but it's a salt. It's made up of an anion and a cation bonding together, although the anion is polyatomic. So this is sodium carbonate, right? How about this one? So CO3, and then the 2 here comes from the upper end. So this should be the carbonate ion. Carbonate ion, and then it is mixed with water, AQ. So how should we name it? If your answer is carbonic acid, then you are correct. Okay, that's carbonic acid. KMNO4, this is potassium, and this is the permanganate ion. So potassium permanganate. HClO4AQ, this is perchloric acid. H2SAQ, so binary acid, and it is mixed with water. So what do we do if you have binary acids mixed with water? We attach the prefix hydro and then change and add ic. Okay, so that's why you have hydrosulfuric acid. How about this one? H3PO3. So no AQ, that means if it's in its pure form, not mixed with water. So that's just hydrogen phosphide. Okay, so PO3, 3 minus is phosphide, the lesser counterpart of the phosphate ion, which is PO4. This is copper 2 sulfate. Again, there should be no space there. Copper 2 sulfate or cupric sulfate. PbCrO4. Okay, so if you notice, these are elements which have variable charges, so be very careful with them. Okay, because the rules for metals with variable charges still apply in ternary salts. Okay, so that's lead 2 chromate or plumbous chromate. Okay, so the charge of the chromate ion is 2 minus. And this one, this is the oxalate ion. So you have oxalic acid. And last one, HI aqueous. So same scenario here. So binary acid, but it's mixed with water, that is hydroiodic acid. Okay, so those are the few examples for chemical nomenclature. Okay, so the key thing here is if we know the names or the formulas of a particular compound, it will be very easy for us to get to know what composes them, okay, and predict what their properties are, okay. And if we know them, we can also know their practical uses, their benefits, or the harm that they can cause. So what's in a chemical name or what's in a chemical formula? It actually gives us power. Names give us power, okay. So that's all for chemical nomenclature. You enjoy the rest of the day.